Hello, I am Faisal again. Today I have taken a very bold step of trying to develop a decoupled thermomechanical simulation model to show you guys how it is done from scratch, almost scratch. What I want to do is I have some simulation models, so I will be using some data from there so we do not waste too much time here and there, and I will try to develop a model from scratch so I can show you guys how I am doing everything. Plus we are able to learn how to tackle the errors along the way and do things in a way that the simulations are doable. I am doing this because in the past several videos I received a lot of messages from people that they were not able to directly follow the steps which I showed, and they were not able to run the simulations as they were expected to, and a lot of them asked for the original files which I shared with them. So of course you can always ask for the original files of the simulations which I show here in my videos. But yeah, we will start with developing a model. I have only copied a thermomechanical material model from the other file so that we do not have to define it here. For a decoupled thermomechanical model, what we are expecting is it can be both ways. So it can either be a thermal model first and then using the temperature definitions in the mechanical model later, or it can be a mechanical model first and then using the mechanical deformation stresses or strains in the thermal model later. Here we want to run a thermal model first and then use the temperature values in the mechanical model later. To start with something like this, it is always quite complicated. So instead of going for rectangle this time, I would like to go for a cylinder, and that adds some advantages and it has some disadvantages, but we'll call it a sample, and it should be 2D planar, deformable shell with approximate size of, we will say, let's say 2. And I want to make a shell of certain outer diameter and certain inner diameter. Let's say the outer diameter, the outer radius of this shell is let's say 500 millimeters, and the inner radius is, let's say, 200 millimeters. So yeah, this is our block, and what I want to do is I want to cool it from outside and heat it from inside. And when we are heating it from inside, I want to apply 2 thermal cycles. So it will heat up and then I will remove the heat, so the temperature should dissipate in some time, and then I want to apply another cycle of heating. So there are 2 cycles of heating. You'll see how it goes, but that is my idea. And outside it is continuously being cooled, let's say maintained at 25 degrees centigrades. Maybe there is water flowing outside and there is hot gas inside, or whatever the case is, but we are considering this as a thermal analysis. Now, to make this sample meshable later, what I would like to add here is I would like to partition this face by sketching these two lines here. You will see what I'll use them for later, but they're super helpful. And then what I would like to do is I would like to create a section, a new one. Let's delete it. I would like to create a section, homogeneous section, steel, solid, continue, material, okay, and then assign this section to this sample. Simple and easy until here, and then I want to assemble it. This is coming in from the old one, so I am importing it, and okay. Then I am defining a step which is heat transfer, and I'm naming it temperature, and the time period is, let's say, we'll modify it later, but let's say it is 10 seconds. The simulation is transient. Increment is maximum number of increments can be many. Initial should not be more than 0.001, and minimum is 1e minus 10, and maximum cannot be more than 0.5. Maximum allowable temperature change per increment is it depends completely on how high a temperature we want to achieve, but let's say it is not more than 20. And so basically for now what I'm doing is I am just starting to design a simulation model, and after inputting everything, after running the first try, we will see what results we are getting, and then we will tune these things usually in the later section. So for now I'm just defining kind of realistic values, but probably we will change them later. Okay, let's reduce the size of the tree. Then in the field output, what I want to get out also is nodal temperatures. Heat flux vector usually not needed, reaction flux is not usually needed. Okay, so these are the outputs which I have requested, and in the history output what I was select is nothing. Then interestingly, what I would want to do is I would want to define interaction property, and then film condition. It can also be inside and it can also be outside. For convection, we will see that later. What I would also like to do is I would like to pin it from some place, mechanical, and then pinning. So I would like to pin it from here, let's say, and then what we need to do is we need to define loads, and we need to define the film conditions. This is something which I will look in the other simulation model, and then we'll define it here. So I have heat flux amp, heat flux amp, and then I'm just defining it here. So it is starting from 0, it is ending at 0.025 for 2 cycles. I also want to see what is the heat flux. It is 5.3 E9. It is temperature, surface heat flux, thermal heat flux inside 5.3, or let's say we make it 5E9 and use this. So we have defined a heat flux here. What else I want to see is defining the surface film condition for cooling. And not defining anything outside. E6, 5E6. And then what I want to do is I want to define interaction surface film condition, and I want to define it on this surface 5.4 E6. It was instantaneous. Sink temperature is 25. Sink amplitude is instantaneous. Okay, so basically this will help us keep the surface to define an appropriate temperature. There are different conditions for different temperature conditions. What I am doing here is I am just using some values from other simulation to just quickly have an idea of how this is done. And then what I want to do is I want to mesh it. For meshing we need this mesh controls, all of them chord structured. I want to mesh it structurally and want to assign this, this, this and this. Do not allow by number. I want to define 100. Seeds seems quite small. Let's say define 50. Seems okay. Let's reduce them a bit. Let's say 40. Seems okay. And then what I want to do is I want to mesh it so that mesh is more or less structured, and for that I want to assign bias, flip bias in this direction, and then constraints do not allow, and by elements I would probably 20 would be okay. Okay, so this distance and this distance, this is smaller, this is much smaller, so I'll change it to 10. I'll change it to 15. Bias ratio is quite high. I will change it to 3. Yeah, so I basically applied bias for these mesh points, so you can see that this distance and this distance is more or less same, and then this distance is more or less same. So when I will use these seeds with structured mesh and select the regions, select standard linear heat transfer mesh, and then mesh the body, you will see that I have a very nice structured mesh. So elements are larger here, smaller here, with still aspect ratio not perfect, but quite close. So when I would run my own simulations, I would still tweak it a little bit. For now, I think this is fine for our initial run. And then I would like to create a job with name thermal so we can understand it and remember it, and then submit it, and then hope that it will run fine. Oh no, this is something which we did wrong. What I am doing is I am defining amplitude for 0.025, and my step time is quite large, 0.025. With this comes the problem of initial increment. If this is 0.025, increment should not be 1e minus 5. Let's say start from here, and maximum should not be 0.001, 0.025, yeah. And then maximum allowable temperature should not be, okay. And then we submit it again and see how it goes. What I'm expecting is that there will be a temperature rise and then a temperature drop, and then again a temperature rise, and there our simulation will end. So the temperatures have risen to 743 degrees. That's great. And when I look at the frame by frame simulation, we see that there is a temperature rise, okay, and there is a temperature drop. And then there is a temperature rise again. Cool. Okay, and then the simulation stops. Perfect. What I would also like to see is I would like to track the temperature here. So I will select XY data, field output, continue. And then there is only one thing, unique nodal, not temperature, nodal temperatures. And then I would like to select this node here and then plot temperature. So we see that there is a temperature rise and then a certain drop in the temperature, and then there is a rise again. And yeah, our simulation ends here. What is important for me in this simulation also is I want to monitor it, and I want to see that there were total 89 increments in step 1. So I would write it down. Step 1, 89 inks. And that is important when we will want to use this ODB. So basically this data is stored as an output database file in the working directory. And now I would like to make a mechanical model. And in the mechanical model, I would apply a certain load in a certain direction, and then we will see how this model runs for that certain load. Okay, I will copy this model so everything else remains the same, mechanical. And so the component will remain the same, the material will remain the same, the section will remain the same, step will change. So I would like to make a static general step this time. Non-linear geometry time is again the same for which we used for the thermal analysis. Maximum number of increments is this, and here we will use the same conditions for the mechanical analysis as we used for the thermal analysis. It was 1e minus 5, it was 1e minus 15, and maximum was 0.001, not more than that. And then field output requests, what we want to do is we want to do pre-selected defaults plus nodal temperatures, because we will see if the temperatures are also coming in and being recorded and things like this. Then in the history output, usually the defaults are selected, okay, and in the interaction we want to delete this film condition. We do not need any interactions, we do not need heat flux amplitude, but we will need some load, and there would be some load amplitude. So at time 0, amplitude is 0. At time 0.025, it is 1. And the load here also cannot be heat flux. Boundary conditions are okay. The load is pressure, which is we will apply on the internal surface. Oh, step name is still temperature, okay. Pressure, and we will define it here. And the magnitude is, let's say it is 200, or let's say 500 megapascals. Amplitude is load amp. We did not need this, we could only just directly use ramp, but let's say we do use it. And then what we want to do is we want to define the predefined fields. Yeah, this is an important step. So in the step, let's change the name not to get a confusion. I have changed this to static general, but the name remained the same, so I will rename it to mech, so we know predefined fields now in the this, and then we will name it temp. We will select others, temperature, continue, and then it asks for the fields to select. I have selected all the fields, and then there are two possibilities. So the distribution can be direct specification, where I apply a certain magnitude, but I want to use it from, because it was transient, so I want to use it from the output database file. The file name is thermal. Begin step is 1, begin increment is 0, end step is 1, and end increment is 89. And here, if both meshes are same, then you can choose that the mesh compatibility is compatible, so element to elemental comparison is also the same, but you can also choose the meshes are incompatible, and then set these ranges that how incompatible are they, so it can directly use the temperatures in this model. Just for the example sake, I am using this. If it was a fatigue crack propagation analysis, I would have chosen the same meshes and then used a compatible thing, because that is more convenient. But in this case we are using, let's say, incompatible. But although the meshes are compatible, I'm not sure. We can use both in this case, but let's say we use incompatible. So I have defined a temperature predefined temperature in this model from the output database file which we earlier recorded. So this is a pure static general model, but we are defining temperature, and therefore it becomes a decoupled, therefore it becomes a thermomechanical analysis, but a decoupled one, because we are not defining temperature in this specific model. We defined it in earlier model. Complicated, no? That is why it took me so long to make this job and run this simulation. So let's say we want to define it here, and we submit. Let's hope that it gets submitted and we get some results. Oh yes, oh yes, oh yes. There is an error. It is nice that it gave us this error, because it says that invalid load type on element 1. Load type is not valid for element type DC. So what we did wrong was, in this case, we did not change the mesh type. So standard, it is not heat transfer, it is plane strain or plane stress. It is plane strain. That's it. Plane strain. And then remesh it, and then submit it again. Quite interesting, because now I am defining a pure mechanical system, and it is taking the thermal data from the previous simulation. As you can see here, it would be the same as which we saw earlier, and then I am applying a mechanical load, and that mechanical load is seen here, and the effects of how it is deforming the component. Coordinate system, create cylindrical. I want to see the not the meshes but the stresses in hoop and radial and those directions, and therefore I am defining this cylindrical coordinate system. Results, options, transformation, user defined. Okay, and then when I want to select S11, these are radial stresses, and S22 is hoop stresses, and S33 is horizontal stresses, because we defined plane strain, so there would be some stresses in this direction as well. And this is then shear, which we are not quite interested in, but let's say this. So here we see that there is so we were able to successfully run our decoupled thermomechanical analysis, in which what we did was we defined a thermal analysis first, with only the temperature attributes. We ran the model, we recorded the file, and then we used that file in the mechanical analysis as a predefined field setup, and yeah, successfully finished the mechanical simulation with the thermal analysis. Let's do some post-processing to see the interesting results, because the material here was at very high temperatures, so this must have become a bit softer, and when the material is softer, the it deforms and there are less stresses but more strains there. And there is also a transient flow, so we will I'm not sure what we are expecting here, but let's see. With temperature, I want to record not meshes, let's say or meshes, stresses on this internal element. And we see that this is the stress here plotted on this axis, and this is the temperature. So with increasing, so we have started applying pressure. So if I record pressure, it would be linear. Let's also plot that. It is getting interesting. Pressure, I'm not sure if it is this pressure or it is some other pressure, but okay, at least one entity should be selected. I want to select this entity. Plot. Oh no, this is resultant pressure, therefore it is showing like this, but what we did was we applied linear pressure. So maximum pressure was 500 MPa, which should seem something like this with 500 MPa here. And then we see that initially, due to applied pressure, the stress increases, but as the temperature increases, the material becomes softer, and therefore the stress at that element drops to a certain limit. And when the temperature drops, the stress starts increasing, and then it increases to a certain limit, or maybe not. We can also see results on the path for different times, and probably there we will be able to see some difference of results. So let's define a path, and a work to be carried out with patience. So we have defined this path, and then what I would like to do is I would to get data on this path at the last frame. What I would like to get is, this is S11, so this is radial. Oh, so we were getting radial stresses there. Okay, so this is radial stress, and it goes like this. So it is quite high at the internal side, and it is almost zero outside. And then when I want to see hoop stresses, we see that hoop stresses are almost zero to a certain thickness because it was at higher temperature, and then they are quite high where the temperature field finishes, and then they tend to drop to nearly zero, but they are never zero. And if we look at the temperature distribution, we see that this is the temperature distribution, and hoop stresses exactly follow this temperature distribution pattern. So yeah, this is a simple decoupled thermomechanical analysis, which I think would be useful for many The advantage of this, if you're able to perform this decoupled thermomechanical analysis, the implications are profound. So you can, if you want to run multiple thermomechanical simulations, what is easier is that you define one. It depends on what is changing in your model. If the thermal system is remaining the same and you just want to select different boundary conditions, mechanical boundary conditions, and want to run simulations, it is convenient to define one thermal model and use that ODB for all the mechanical systems, because the mechanical simulations will run much faster and you will obtain results much quicker than if you will run thermomechanical system as a whole every time. What it also does is it gives me an additive advantage of defining residual stresses, and this is something which I am building on. So in the next step, what I would like to show you is what we did in our recent article which we published. So we ran quite a complicated, with residual stress, thermomechanical fatigue crack simulation model, and extracted some really interesting results for auto-fretted gun barrels when fired multiple times per minute. And this understanding this decoupled analysis will help you get through that as well, and I hope you will get some information out of this video and you will be able to apply it in your research and your methodology. Do not forget to check out my Google Scholar page, ResearchGate page, and other videos if you're interested in them. And yeah, happy simulations. Bye.